Hey there, I thought to do a video log while working on these two units. So they were manufactured in the late 80s and really well built. The unit on the right is HB 8647A, strictly a sinusoidal signal generator, frequencies from 260 kilohertz to gigahertz with AM, FM, and phase modulation. And unit on the left is HB3314A. It's a multimode function generator. It features frequencies from 1 megahertz to 20 megahertz, limited on the frequencies, but it has multimode of sinusoidal, triangle, and square waveform functions, as well as arbitrary, which would be user programmable waveforms. Both of these units can be operated remotely with software and cable from a PC. So both units were introduced by Hewlett-Packard in the mid-80s, and they were still in production into the late 80s. And their operational status is currently unknown. I think since they were stored in an attic for 10, 15 plus years, it would be a good idea to open them up for a visual inspection. It would be prudent to isolate their power supplies and test their voltages before a full power on. So with that, let's go ahead and take a look inside each unit next. Okay, so the first unit up is the 8647A. We're going to go ahead and take the top cover off. The front panel is recessed, so it's really easy to set the unit on its face. And I've already removed the screws, 9 screws, 5 in the bottom, and 4 on top. And with the screws removed, I'm going to go ahead and take the case off very gently. It does get stuck a little bit, just got to be a little bit patient. I'll show you the reason for that is because the feet have small tabs that they stick out. So you just want to be careful. With the case removed, notice the second top shield that can be removed. I've removed most of the screws. I'll remove the only other 2 screws left. Another nice thing about this unit is that all screws are identical. Screws not to be removed are marked clearly. Okay, with the top shield removed, we could have a look inside. I've done a fair amount of research and reading on this unit. As you can see, the old Motorola 68000 microprocessor is visible. That's on the main board where the signal is actually generated and then later converted to analog. These units come by default with 3 assembly kits installed. The reference kit, the synthesizer kit, and the RF output. The reference kit is where the actual 10 megahertz reference signal is generated, and the synthesizer kit is where the signal is converted to analog, and the RF is the final output. One thing that I've read quite a bit about on different blogs about this unit is that the power supply, which is a switching power supply, has issues specifically with one capacitor. So we're going to go ahead and remove the power supply. I've already taken some of the harness off. I'm going to just take these 2 screws off and start removing it. Now the power supply has its own shield. We're going to go ahead and take off the first 2 screws on the top. And I've already removed some of the screws on the side here where it's held in place. Okay, and so with the harness removed and all the screws removed, we can gently guide the power supply out, very, very gently. It's a tight fit, so you're just going to have to be patient. This unit can be tested in isolation to make sure that we have the proper voltages. On many of the blogs that I've been reading, where the capacitors fail and in some cases have actually exploded, is this paper capacitor inside here. So I'm going to take some closer look at this and see what that capacitor actually looks like. And with the power supply removed, I'll show you the main harness from the main switch. Is actually zip tied on the corners. I had to remove one of the zip ties, which I will later replace. And this is where we see the battery. That's battery for the settings of the unit when it turns on. This unit does have some calibration data that's stored on ROM, and then on power on supposed to be pulled into RAM to use. So hopefully all that data is still good. And with the power supply removed, we have good access to the backup battery. We could have a look, make sure that still puts out 3 volts. So that works out really good. I've taken some close-up pictures of that capacitor. It's a paper capacitor that it's sealed in epoxy. And the problem with these capacitors is that over time, if they're made from cheap material, they could crack and allow moisture inside. So I think this capacitor is bad enough to replace it right now. To do the replacement, we take the shield cover off from the switching power supply unit. So it was fairly easy to remove that capacitor with a little bit of solder wick. And you can actually see that capacitor is really old and indeed cracked and bulging. I can read the voltages and the values, and it's really prudent to just replace it before testing this power supply in isolation. So with that, I can't go much further with this unit until a new part arrives. So we'll move on to the next unit. All right, so moving on to the next unit, the HB3314A. Older technology, but it seems to be in pretty good shape physically. Still has the quick built-in reference cards attached. We're going to go ahead and take the 2 screws holding the handle in place off in order to take the cover out to have a look at the condition inside. The rear bracket comes off by tilting it upwards. And now with the 2 top screws removed, it's just a matter of pushing gently on the top cover. There you go. And it comes right out. So I've done a fair amount of reading and research on this unit. I'm going to go ahead and turn it toward the camera and tilt it so we can have a better view. Okay, so inside there are actually several boards that are underneath each other. We're looking at the top main board where we can see it's an old Motorola 8-bit microprocessor chip that is quite old. It's dated 1989, so hopefully still works, along with his 4 megahertz crystal oscillator, several memory chips, couple of factory ROM program chips, and a CMOS RAM chip. Now this is for holding on to instrument settings so it can be recalled upon power on, and also for user-defined data, user-defined vectors for its arbitrary waveform feature, and also a battery backup to hold on to that memory. So we will check the voltage on that battery to make sure it's still good. Now you also notice these thick white lines that are printed on the silk screen. They are indicating boundaries and functional blocks. And the name of each block is also nicely printed. So in the service manual, which is thankfully available online, most of these functional blocks are explained alongside with circuit diagrams. So I'm really happy that there is a fair amount of good information available. Anyways, my plan to test its power supply in isolation is really not feasible because in this unit, the power supply is integrated in the main board. It's not a complicated switching power supply like the other 8647 we were looking at earlier. This power supply is fairly simple. We have the transformer feeding into the main board. We have a diode, bridge rectifier, a couple of smoothing capacitors feeding into voltage regulators. I can test the capacitors to make sure that they're shorted, and I think for now I'm going to go ahead and isolate the transformer to be tested later by pulling this harness out. So with that, we can go ahead and take a look at the rest of the unit. This main board tilts up on these 3 hinges on the back. Just need to remove these 3 screws in the bottom, 2 of which I have already removed. So we'll go ahead and remove this last screw so we can rotate the top board up. Okay, so we have now lifted up the CPU controller board. It doesn't go all the way to 90 degrees, so I've tilted the unit slightly to make sure that it stays up. In the service manual, this board that we're looking at is referred to as the mode board. And there are still more boards underneath that we're going to look at. Just a quick note, a brief high-level overall theory of operation. Unlike in modern digital designs where signals are fully computerized and synthesized, this function generator at its core is an analog device. At the very bottom, where we're going to look at soon, there are sensitive analog circuit boards that can generate a pretty clean triangle waveform, which are later converted to square waves and sinusoidal. But the main key idea is that the required precision of those signals are, in fact, fine-tuned by the CPU, mainly by varying the voltage or current on the analog oscillator. So the CPU, the microcontroller board, the microprocessor board, the CPU engages in this fine-tuning, kind of like adjusting the knob, so to speak, to ensure that the signal that's being produced on the output meets the user expectation by around 99.9% or better. So, although the signal is generated in analog form, there is precision calibration of the signal's amplitude, shape, symmetry, and frequency that's achieved and controlled by the microprocessor board, and all that controlling is done mainly via this interface board here that controls all modes of operations like phase lock, sweep, gate, arbitrary modes, etc. And that's why this board is called the mode board. So like I said before, it's very old tech. The CPU is the very, very old Motorola 6800, the great granddaddy of the old Motorola 68000, running at 1 megahertz. We mentioned the 4 megahertz crystal on the main microprocessor board, but that's the main system clock, and there is a divide by 4 for the 6800. So it runs only at 1 megahertz from 70s and 80s. But as you can see, it's really built well and solid, and a lot of thought and design has gone into it. Well engineered by HP for its time. So I'll be tickled and really, really grateful if it still works. In any case, this board also looks to be in very good shape. Just needed to vacuum out some dust. Had a close examination of all components. Did not find any issues, no residues, no corrosion. So with that, let's go ahead and move on to the final boards in the bottom. So to expose the bottom, we have to turn the unit over, not too heavy. It's around 16 pounds. And unscrewing this single screw on the edge of the cover will extract the cover automatically. I think it's kind of cute that part of the transformer pokes out the back. And I like the mesh filter in front of the fan. The screw will stay inside the cover. It has a catch on the other side. So with that, we could just slide off the cover to expose the belly. So again, we see the very thick and solid aluminum frame. This frame and the overall shape of the unit was designed by HP with certain options in mind. HP offered a variety of optional hardware kits, for example, to allow a slide and secure it into a rack mount configuration, or carrying handle kits with rear feet stands for mobile use. Okay, we're now looking at the two final boards in the bottom. We have the generator board and the amplifier board. The amplifier board can be lifted up. It can tilt on these two hinges here by just pulling up on these snap downs. Just pull up on the release and just watch the cable, and it can be lifted up really easily. And it can also slide off the hinges. I'm not going to do that right now, but it's really convenient. And there is room here for an optional high voltage amplifier that can be installed on these screw footings. One more board that we can't see very well. It's behind the front plate where we have all the front panel display and all the controls, all the user controls are. But we're not going to go that far unless we have to after a power on test. So hopefully all that controls are working good. Okay, so we're now mainly on the analog side of the unit, and the triangle oscillator that we talked about is produced underneath this shield, which I did remove earlier just to have a look and took some pictures. So most of the parts that we see are, well, with the exception of a couple of custom chips by HP, most of the parts that we see are discrete components like transistors and transistor arrays on ICs, op amps, and comparators. And so looking at all this, I couldn't help but to get more curious about the inner workings and how the heck can a processor control an analog oscillator, and how does it all work? And the answer that I found is fairly simple to understand. It's pretty neat design that I can brief you on. Let's have a quick look at a few diagrams in the service manual together. Okay, so just a few minutes on this and then we'll start testing the unit. Looking at this high-level block diagram, again on the PDF service manual, and this circle portion here, which is the triangle oscillator, is further explained in another block diagram down here, which is a simple design, is recognizable as an emitter coupled circuit, also known as long tail pair. So these two transistors, Q1 and Q2, are connected as a differential pair amplifier, or diff pair for short, except interestingly with a capacitor across the collectors. And there are three current sources, two on the collectors labeled as I up and I down, and the third one on the coupled emitters. So to understand how this circuit can generate triangle waveform, let's compare it to a basic differential pair. I've drawn a rudimentary circuit diagram for a typical differential pair on the margins here. And as a reminder, on a differential pair, we normally have the outputs on the collectors here, either from one side or differentially. But we know that these currents through the collectors from the supply define the differential voltage on the output. Basically the output gain or amplification is a function of the difference to these base inputs. And to stabilize the voltage gain and to make the output amplification linear, we don't use a current limiting resistor here, but instead we use a current source on the tail here for better controlling of the bias on the tail current, which also reinforces common mode rejection. So now, keeping those principles in mind, looking at this diagram here, in this case, we're not amplifying the inputs to the bases on the collectors. These base inputs simply alternate between being either on or off, which simply change the direction of charging and discharging this capacitor across the collectors. And still using the differential currents through the collectors. However, these collectors are not directly connected to the supply, but instead they are connected to these current sources, I up and I down, which means that the charging and discharging of this capacitor will be smooth and linear over time, just like an integrator circuit. So essentially, this circuit is a differential integrator, and the differential voltage across the capacitor is in fact the output of the oscillator, which would be a triangle-shaped signal with smooth ramps going up or down, depending on which of these transistors is on. Now we also see this feedback loop labeled as common mode loop, and this is for adjusting the output common mode voltage at the integrator here, which is controlled by slightly adjusting this current source on the tail here. It's being fed from the output of the integrator through this resistor divider through some buffer circuits shown here as just buffer symbols. So this is a similar idea to controlling the bias on the tail current in a differential pair. Adjusting this current on the tail here controls the overall gain and controls the overall offset voltage of this differential integrator so that it can be kept steady with respect to this fixed reference voltage here, maintaining a certain offset level, and to keep the voltage oscillation in the middle of the top and bottom voltage supply rails. Although here they're only showing ×1 or unity, there is a ×10 mode as well, which can also change that offset voltage for certain modes. But one important point to note here is that the amount of charge on this capacitor is not controlled by which transistor is on, because these two transistors can only control the direction of charging, not the amount of it. The amount of charge itself on the cap, we know, is a function of how much current goes through the capacitor. And in here, those currents are strictly sourced through the I up and I down current sources. So therefore, the higher or lower the magnitude of difference on these current sources, I up and I down, that difference will drive the differential voltage across the capacitor, ramping it up or down. So basically the idea here is that with precise control over these current sources, we can have precision over how steep or gentle these ramps of the triangle oscillator output would be. And these on-off signals to the base inputs, S up and S down, provide control over the direction for either going up or down on the voltage ramp. Pretty cool and simple to understand. And of course, these output signals are not final. They're converted into differential currents that are then fed into a signal shaper chip and circuits, where the final signal shape, for example, sinusoidal waveform, can be generated, and also where the CPU can control the amplitude. Now comes the question, how are these I up and I down current sources precisely controlled? And that's where the CPU comes in. But with the help of a special DAC chip, a digital to analog custom-made chip by HP, which enables the CPU from the controller board to digitally program the precise required current levels. So that DAC chip is essentially designed as a current source that is digitally programmable. And so we get in the big picture here that being able to precisely control these charge currents and switching the direction of charging, we can see full control over precise duration and precise angle of each up and down ramp. In fact, if we think of these transition points as like a vector on a graph, then we can see easily that all the user has to do for defining an arbitrary waveform is to basically program the height or the amplitude of each of the desired vector points into the RAM memory. So then the CPU can read them and program those vectors into the DAC chip, where they will then be converted to precise current levels on the capacitor. Pretty cool. And normally in continuous mode or in free run mode, these currents across the capacitor are kept symmetrical at a preset level for a desired oscillation at a continuous frequency. But regarding these two signals, S up and S down, and where do they come from? They're actually coming from feedback loops from the outputs here. The T up and T down outputs here are fed into a hysteresis circuit in another stage. And that is where these consistent trigger signals are produced at certain voltage levels to switch these transistors on and off in order to determine the exact timing as to when they should switch to change the direction. Here's another block diagram of the differential integrator or oscillator here. And we can see all the control signals easier. I've highlighted them in two different colors. We have the I up and I down current sources that come from the DAC chip feeding into the integrator, controlling the ramps, and the output of the oscillator is fed into a transconductance stage where these differential voltage outputs are converted into differential currents that are then later fed into the sine shaper chip and circuits. These two output T up and T down are also fed into the hysteresis comparator, as we saw before, to generate the S up and S down trigger signals into the integrator. These additional controls are used for non-continuous mode that can interfere with the production of the trigger signals. And overall, this block has a critical timing role. So we'll take a look at some of the details of this circuit in a minute, which is basically a Gilbert cell used as a signal comparator, producing these consistent timing signals to the oscillator. Although in non-continuous mode, in some non-continuous mode, several up and down are used instead, and more on that later. But in continuous mode or free run mode, these outputs, trigger signals, are actively fed back into the integrator, as we saw earlier, to trigger the bases of the diff pair transistors. We can see on this oscilloscope capture the output of the triangle oscillator changing direction at exactly the rising falling edges of the S up and S down trigger signals, which is adding precision to the switching intervals. And these same sharp signals are also used as a synchronizing signal throughout the unit as a sync signal. For example, to the sine shaper chip as shown here, or we'll see in a minute also for sync output. Now, lastly, how to maintain accurate frequency. So for that, the output signal frequency is calibrated by the CPU. And in fact, fine-tuned every time the user makes a change. We can see how in this block diagram. So zooming on to where I've highlighted the familiar circuits, we have the DAC chip, the oscillator or the integrator, the sine shaper, and we can see that the main synchronizer here is the hysteresis comparator with these identical timing signals that are also buffered to be used as sync output and as a feedback for calibrating the frequency. So following that back here, we can see the calibration is done by comparing the frequency of this sync signal against an onboard reference frequency, which in this case is the same crystal oscillator for the system clock, except a fraction of it at 10 kilohertz as a precise master clock. And the actual comparing is done by means of phase detection, just like a phase lock loop circuit, with a combination of these frequency dividers as clock multipliers that are programmable by the CPU based on the user selected frequency. And once the difference in frequency or phase has been detected, then the amount of correction is ultimately fed back digitally into the DAC chip in order to adjust the current sources feeding into the oscillator in order to bring it into sync. And this feedback loop and adjustment may need to be repeated a few times while the CPU controller tries to bring the frequency into lockstep. And if for some reason is not able to, then the CPU may, after 5 tries, display a calibration error, like indicating that it cannot steer the frequency to correct it, or that even after applying all the corrections, it's still off by a certain percentage, or that it cannot sense any frequency at all. And by the way, for amplitude calibration, there are similar processes and errors, so let's hope we don't see any of that. And of course, the actual circuits are complicated, and I will research and learn more details over time, but grasping the high-level operation has been helpful to make it easier to understand the circuit diagrams. So like here, I'll share with you briefly the differential integrator or the oscillator under the shield. And we can see that there are several capacitors here instead of just one. And that's because there's a wide range of operating frequency. So each capacitor here is for a specific frequency range that can be switched in and out of the circuit depending on the frequency selected by the user. These switches are actually reed relays with these flyback diodes for coil suppression, and interestingly, based on the photos I've seen online, they seem to have been updated from early 80s to late 80s. Also, instead of one, there are 2 differential pair of transistors. This pair here is only active when operating in non-continuous mode, like the arbitrary mode. And these base signals labeled as servo up and down that was mentioned come from a separate control and timing circuit that can hold each of these transistors in either up or down state, and that's in concert with the DAC chip when initiating a new vector with I up and I down generating a ramp. And when in continuous mode, this pair of transistors are active instead, which we've already talked about, where these trigger signals S up and S down are fed in from that hysteresis comparator. So we might as well have a quick glance at that now. It's this circuit here with this Gilbert cell chip at the center, fundamentally used as a signal comparator. And these 2 circuit blocks that I've highlighted in blue are nearly identical circuits holding each side of the Gilbert cell at a constant current and voltage, depending on the modes of operation. There is this easier to understand block diagram version here, where all this area on the left and the right have been sort of summarized as current sources to hold the 2 sides of the Gilbert cell at a constant voltage. 2 diagrams are shown here for both continuous mode and non-continuous mode, like gate mode or half cycle mode, where these additional controls can intervene with the production of the S up and S down trigger signals to the oscillator so that it can be instantly turned on or off or held at a certain level. But regardless of modes of operation or the shape of the signal being produced, continuous or non, whether the S up and S down are actually being fed into the oscillator, or let's say for arbitrary mode, servo up and down are being used instead, we see that these same trigger signals are always buffered and available down here, marking the beginning and end of each cycle, producing the sync up and down signals. And that's because we always need to generate a consistent synchronized signal to be used as a sync output for external use and as a feedback for frequency calibration. So that's sort of a broad brush, high-level overview of how it's supposed to work. Longer than a few minutes describing an old equipment, but I thought you might find it also interesting. In comparison to modern units that use direct digital synthesis with fast memories and fast CPUs and so on and so forth. So with that, we'll move on to start testing the unit. So the first thing I just did was to test the backup battery and luckily it still puts out 3 volts, so that's great news. Next, I'm going to use my analog meter to test the smoothing capacitors here. I have it connected to a common ground, so all I need to do is to connect it to each side of these capacitors. For reference, this is what a short would look like. This is the ground. I've already calibrated the meter, and on this side of the capacitor we have a nice charge. I'm not too concerned about it getting fully charged because it's in circuit. I'm looking for a short here. Again, this would be a short on this side, which is the ground, and on this side it has a nice charging behavior. So they seem to be okay. This other smoothing capacitor is for 5 volts. There seems to be a little bit of voltage there from the backup battery. Seems to be sitting around 0.5 volt or less. This is being fed from the backup battery, so I'm going to trust that for now. Okay, so before power on test, let's have a quick look at the circuit diagram here. There are 3 voltage regulators that I've highlighted here. There is plus and minus 15, and there's also a 5 volt that I just mentioned. There is an overvoltage protection that seems to be able to trigger the processor reset line. This is our rectifier circuit and the 2 smoothing capacitors that we just tested. And this is the plug that we have disconnected in order to isolate the power transformer in order to isolate it for testing. On the other side of the transformer, we got the switches to select for 110 or 220 options, and the fan is directly connected to the AC outlet. So for this test, we should hear the fan come on, and we should be able to measure at least 24 volts on each side of this transformer with respect to the center tab. And if all that goes well, then we could connect the rest of it, and with the 2 meters that I have, we can simultaneously measure the minus 15 and the 5 volts as a way of monitoring the voltages. So let's go ahead and start with that. Okay, so I've just connected the AC outlet, and we'll put the meter on 200 AC, and we turn on the unit. That sounds good. And hopefully I can measure 24 volts coming out of the transformer. 25.4 on one side. .4 on the other side. So that seems to be good. I'll go ahead and power it off. So next I'm going to set my analog meter to 10 volt scale. So 5 volts should be right in the center. And there's already a 5 volts checkpoint tab here, so we could use that. And for minus 15, I'll use the digital meter. We'll use the same ground, and we use the minus 15 checkpoint on the board. And we take the meter out of AC, put it on DC, and we will connect this back on. And with a little bit of luck, hopefully we'll have a safe power on. If all goes well, there should be a countdown, so wish me luck. And there is a countdown. And I don't see an error. We got the 5 volts and we got the minus 15. Okay, well, this is great. No smokes or sparks. And no calibration error, and I'm glad to see this appears to be a successful power on. So I think I'm going to wrap up this video for now. I will make a part 2 video as I learn more about each unit sometime in the future. That's it for now, and we'll see you next time.